Welcome to Educator.com and AP Statistics. In this first lesson, we're going to be talking about constructing and interpreting graphs. So just an overview of this lesson. We'll first talk about categorical data and graphs that you'll use for that type of data. Then we'll talk about quantitative or numerical data and the graphs that we'll use for that. And then lastly, we'll just talk about how we would describe data using a graph. So let's get started. So categorical data. So categorical data is for variables that have categories. So you can't necessarily put them in order, and they don't really often have numbers. So an example here is with this type of sports that people play, right? Swimming, gymnastics, tennis, these are all categories. They're what we call qualitative variables. There's a quality to them rather than a quantity or a number. So two really common forms of graphs to show categorical data is a pie chart and a bar graph. So a pie chart you've probably seen before. The percents in them are going to have to add up to 100%, and you can look, and it's kind of a visual way to see, okay, yeah, soccer will have the largest percent, and then the smallest percent just based on the graph looks like it's split between gymnastics and tennis. So that's one way to show categorical data, but actually the more common way is to use a bar graph. So in a bar graph, you have your different categories. So in this case, it's the kind of pet that you own. And then we have the count, or in this case, the number of people that own that type of pet. So notice that rabbit, dog, cat, you couldn't really put that in any type of order. And that's why it's really important that it be in a bar graph or a pie chart, because when things can't be ordered, they need to be in a certain type of graph that takes into account the fact that we can put them in any way and it should show the same thing. So notice, this is really important when you're doing a bar graph, that these bars do not touch. If they do touch, it's a completely different type of graph. So make sure when you're making a bar graph that the bars don't touch. And then generally on this axis, which we call the y-axis, you're going to have a count. And then on this axis, which is the x-axis, you're going to have the different categories. Okay, so let's talk about some more advanced bar graphs, because again, it's really a common one you're going to use. So a really important one to know about is a comparative bar graph. So in a comparative bar graph, you still have your categories on the x-axis, and you still have your counts on the y-axis, but now you have this third field, right? You have this key that's now showing you for each of my categories, I have in this case, three different things, three different options. So in this case, we have a little key that's telling us the year. So in 2003, 2005, 2007. So now we can look at Africa, say, and we can say the count of probably what's sold was much higher in Africa in 2005 than in the other years. Versus North America, it was the highest in 2007. And then we can tell on the whole that it was the highest for all the years in Oceania. So this is a way to add a third variable to your bar, or to your graph. Okay. One other variation on a bar graph is what's called a relative frequency bar graph. So until this graph, we've only seen counts on the y-axis, but you can actually put a percent on the y-axis. So if you have all the different options, right, so all the different colors, maybe this is people's favorite color, and you ask everyone their favorite color, well, the frequency should add up to 100%, right? So let's say we asked 100 people, what their favorite color was. Well, here we see that 37 of the people, or 37% of the people, said that their favorite color was blue, whereas only about 4% said that their favorite color was purple. So it's just a way to turn numbers into a percent. So with n equals 100, it wouldn't really matter. But if we had asked 10,000 people, it might be a lot easier to present this as a percent than having these long bars, right? And then just a little bit of difference at the top. Okay, so let's take it a step further, and now we'll talk about numerical data, but discrete numerical data. So in this case, it's kind of almost a combination between categorical and numerical data, because it's numerical data that can't take on infinitely number of decibels, but in fact it's discrete, meaning we can only have 1 or 2 or 3 or 4, not 4.5, 4.75. So that's why our graphs end up looking somewhere between the kind of graphs we use for a categorical variable, i.e. a bar graph, and something close to what we use for numerical data, which is a histogram, and we'll get there in a second. So a really common one and a really easy one to make is a dot plot. So all that is you put a dot every time there's a number. So this data would look something like 0, 0, right? We'd have a ton of zeros, we'd have a bunch of 1s, and then we'd have no 5s, we'd have 2 6s, right? So if we read through the data, we'd say, okay, I have a 0, I have another 0, I have a 1, I have another 1, I have another 1, I have a 6, I have a 6, right? You'd read through and you'd just pile them on. Now you wouldn't want to make a dot plot if you had decimals, right? Like infinitely many decimals, because then they would never pile on top of each other, right? It'd just be a flat line, but with a really, really long line. So you really only want to use a dot plot when you have discrete numbers, or a discrete number of options. So whole numbers, 1, 2, 3, 4, 5. Okay, another type that you can use for this discrete numerical data is what's called a stem plot, also known as a stem and leaf plot. And the reason it's called a stem and leaf plot is because we have the stem and then we have the leaves. So I haven't written it here yet, but it's really important that when you're making a stem and leaf plot, you put a little key. So your key should look something like this. So you pick a number, let's say 90, and you tell someone that means 90. Another option is that it could have meant, right, 90 could have meant 9.0, which is why it's really important that you put a key. So a stem and leaf, the first digits, or rather the first however many digits are the stem, and then the last digit is the leaf. So what this is saying is that I have 90, 94, 84, 87, 89, etc. So this is a pretty rough stem and leaf plot, and usually it's written from the smallest to the largest, and then it's a good idea to try to order the leaves just because it makes it a little easier to interpret. But you still, from this, right, get an idea of the shape of the graph, and that's really helpful, right? So this is a great graph, as is the dot plot, because you can not only see the actual numbers, but you also get an idea of the shape of the distribution, right? We can see it's kind of shaped this way. If I were to make it a graph, it'd be kind of leaning off to the right. In this case, it'd be leaning off to the smaller numbers, which would be kind of like the left, but we'll talk more about that in a second. Okay, so let's do an example. Make a stem plot of the ages in a college classroom. Okay? So I'm going to make my little stem and leaf. So first I want to figure out what are all of my stems. So I have teens, and I have 20s, and I have a 40. So I'm going to have 1, 2, and there are no 30s, but you can't skip it. Otherwise, it's like having a chunk missing out of your graph. So you'd want to say 1, 2, 3, 4. And then we'll write it out. So we have an 18. Actually, let's write it in order. So we have a 17, we have an 18, we have another 18, then we have a 21, a 23, and a 26. We don't have a 3, so we need to leave it blank. If we had put a 0 here, it would have been saying we had a 30. And then we have a 40. And then lastly, you want to make yourself a little key, so that whoever's reading your stem and leaf plot knows what it means. Perfect. Okay, so let's talk more about numerical data, but now instead of discrete numerical data, we're going to talk about continuous numerical data. So here's an example of exam scores. So we have the points that people scored, and then the number of students that scored it. So technically points are a continuous variable because you can score anywhere from 0 to 100, and it doesn't have to be a whole number, right? You can get partial credit, so it could end up being some number of decimals, or maybe this is the percent that they scored, right? So if this is the percent, then someone could get 93.567%, depending on how many questions there are. So that's why this is a continuous variable, because it can take on any number of decimal points beyond the number. So this is what we call a histogram. And you might notice that this looks really similar to a bar graph. But notice that the bars in this case are touching. So that's what differentiates, like by a quick glance, between a histogram and a bar graph. A bar graph, the bars don't touch. In a histogram, they're together. So make sure when you're drawing it, you have to draw them, the bars touching. Another thing with a bar graph, or with a histogram, is instead of having categories, we have ranges of our numerical values. So sometimes people write it as an actual range, or like in this example with salaries, they'll write kind of the edge, right? So technically this range here is 0 to 20,000, this range here is 20,000 to 40,000, but instead of writing it as a range here, they just write the upper value. So that's fine. Either one is correct, but it has to be that the bars are touching, and with a general histogram, we're going to have counts on the y-axis, and then you're going to have your continuous numerical variable on the x-axis. Okay, so let's do an example. So we are going to use the calculator to make a histogram of ages in the college classroom. So here we have the ages, but I've changed them up a little bit because you kind of have to have more than just a few numbers in order to make a good histogram. So the TI-84 for the AP Statistics class is your friend. You have to get really familiar with it. It's going to be doing a lot of things for you. And on the AP exam, you are more than welcome to use it. You just have to say, if you're doing something where you normally have to do a bunch of calculations, you'd want to say, okay, did this in the TI-84 and tell what command you're doing. Because statistics isn't really math. It's more of a science. It's more about what do the numbers mean? How do I interpret them? Rather than, yes, I can do algebra. So that's why the calculator is going to do a lot of the math for us, and we're just going to get really good at interpreting it and at understanding what the question is trying to ask. Okay, so whenever we have a list of numbers like this, the first thing you're generally going to do is put them into a list on your calculator. So if you're familiar with Excel, it's really similar to that, right? Excel has these columns where you put numbers in, so does the calculator. So, big surprise, this is a statistics class. We're going to go to Stat, turn it on, Stat, and then Edit. So it's the first thing you see, Enter. So now you have these lists, and these are just like the columns in an Excel spreadsheet. So you're going to put the numbers in by typing the number, hitting Enter. So we'll just go through and put all these numbers in really quickly. And you should be doing this along with me. 23, 27, 22, 19, 20, 21, 18, 35, 32. Perfect. So now we have all of our numbers into a list. So it's a good habit, whenever you're in a list, you want to quit out of it. So second quit, which is the blue button here, because otherwise sometimes it'll accidentally put stuff into the list and you don't want that. Okay, so now we're going to make a graph. In order to make graphs in your calculator, you're going to go here to Stat Plot. So you're going to press second, y equals, and then we'll just use the first one. So make sure that's on. You'll highlight over on, and then we'll go down here to Type. So they make it really easy. The type is always going to kind of look like the graph you want to end up with. So we'll scroll over until we get to this little graph that kind of looks like a histogram. And then we press Enter. And then notice that it goes down to just asking for one list. So you're going to tell it where you put your variables, in this case L1. If yours doesn't say L1, right, the little numbers are here, so we can say second L1. And then you're not ever going to mess with this frequency list. You're going to go to Zoom, and then we're going to scroll down until you get Zoom Stat, right? Statistics course. Instead of scrolling down, if you just start to memorize it, you could press Zoom 9 and it would go there automatically. Okay, so perfect. Here we go. Now we have our histogram. So we can kind of trace this histogram even. So we know that this is age, right? You're always going to have to label your axes. So we'll say age, and then you always want to put your units. So age in years, and then this is the count. And then we'll pull this back up, and an easy way to copy this, to kind of trace it, is to press Trace, and then you'll notice that it gives you the range of your values. So here it's 17 to 21.6. So if you're not going to start at 0, it's okay, but you want to put these little dashed lines that show you kind of truncated your graph, that you kind of got rid of the first little bit. So we'll just draw ourselves a bar. and this is 17 to 21.6, and then we see that there are 8, so we'll mark that as 8, and then we'll trace to the next one. So this is 21.6 to 26.2, and actually it might be a little easier because I made this a little smaller than I meant to, that we'll just mark that this is 21.6. Okay, so then we see that this is 3, so it's going to be a lot smaller. And it's really important to try to make them the same width. Okay, then we have, that goes to 26.2. So this is 26.2, and then you'll see that the next one is only 1, and that goes to 30.8. And you probably don't want to put it all in different colors, but I am just so you're seeing it. And then the next one has 2, and it goes to 35.4. So this is 35.4. And that's going to be kind of in between. Okay, then we don't have anything, so we need to leave a space. And then our very last one, 40 to 44.6. And that was 1. So we'll want to make sure that's about the same height as our green one. And there we go. We have a beautiful histogram. The calculator helped us to do it. And the key thing is that you can interpret it. So you can see that most people are around here, and then it kind of spreads out to older ages. And we'll talk a little bit more how to officially interpret it in a minute. Okay, so just 2 other numerical data plots that you might see. So until now, we've always had count on the y-axis when we had a continuous numerical data. You can also have the cumulative frequency. So a cumulative frequency is when it's this point plus everything below it. So in this case, for a test score of 76, we see that there were maybe about 180 who scored 76 or below. Here, for a test score of 105, we see that there were maybe 525 students who scored at 105 or below. So a cumulative frequency plot, which is also called a frequency polygon, can be useful if we want to see kind of at what score it started to plateau, right? Where was the big change in score? So most people didn't score really low. Most people didn't score very high. The majority of people were somewhere in here. Okay, and then just a little change on that, you can have an ogive or an ogive plot, and that's going to be the cumulative frequency, but it's going to be the relative cumulative frequency. So we've turned it into a percent rather than a cumulative count. So here, age at inauguration for presidents, let's say at 55, we have about 50% of all the presidents were 55 or below at their age of inauguration. So this type, the ogive, is often used when we have time on the x-axis, right? Because as time goes along, we're interested in what happened from there beyond, right? Are things changing? Are they continuing to add up? So whenever you're doing a relative cumulative frequency, that's an ogive. Whenever you're doing a frequency polygon, cumulative frequency, that's a frequency polygon. These are going to be much rarer. You're really not going to have to make these, but you might have to interpret them on a test. So it's important to be able to read your graphs. And then one thing to note is that none of these graphs have units, and often they won't, but if you're ever asked to make a graph, you always want to put units. So you always want a title, you always want to say what your x and y axis is, and then you always need a unit. So age at inauguration, you should put years, right? Relative cumulative frequency, make sure that you say that's a percent. Okay, test score, make sure that you say this is points, or maybe it'd be a percent. So you really want to make sure you have your units. Okay, so let's talk about the kind of questions you're going to get in graphical, or that have to do with graphs. So most often they're going to say, describe the distribution. That's a very vague question, right? But whenever they're saying describe the distribution, what they're asking for are the SOCs, spelled missing the K. So the SOCs, if they're asking for the SOCs, they want the shape of the distribution. They want to know, are there any outliers? And then they want to know what the center of the distribution and what the spread of the distribution is. So we'll talk about these three things later. We'll kind of brush on them now, but we'll talk about how to calculate them precisely in a later lesson. For now, let's talk about shape. Okay, so the shape of your distribution. So really, we only talk about shape when we have numerical data, right? Because categorical data, it wouldn't really make sense because you could put it in any order so the shape would change. So we can talk about a shape when we have discrete continuous variables discrete numerical variables, or if we have continuous numerical variables. As long as we can kind of sketch a shape over it, we can say what the shape is. So the first thing you're going to look for is it unimodal or bimodal, or it could even be multimodal if you have enough data points. So that's multimodal. But the majority of AP Stats, you're going to be dealing with unimodal distributions. So then, if it's unimodal, you have to go on to say if it's skewed. So if it's this really nice little bell shape, then we say that it's symmetric. If, on the other hand, it looks like this, and you, as a non-professional skier, would want to ski down this way, rather than jumping off the cliff this way, then I'd say it's skied, or skewed more appropriately, to the right. If, on the other hand, I'd want to ski down this way, then I would say it's skewed or skied to the left, right? So you don't want to jump off the cliff, so figure out the way you want to ski, and that's the way it's skewed. So here, when you'd ski either way equally well, that's symmetric. Okay, so let's do an example. So we're going to describe the distribution of ages in a college classroom. Okay, so we've seen this before, so we're going to just go ahead and go to our list and make sure we have all the numbers in there. So we have all these numbers in, 23, they're all in there, 19, 35. Okay, so everything's in there. So we're going to go ahead and go to our graph. So second stat plot, it's there. Double check, everything looks good. So then we'll say zoom, and we can scroll down to zoom stat, or we could just press 9. And there we go. So the distribution of this graph is that it's skewed to the right, because I would want to kind of ski down to the right. So very easy. Put the numbers in, graph it, and then you can say very easily which way you'd want to ski down. Okay, so let's extend upon our stem and leaf plot and do a stem plot to compare two groups of data. So this is a really common type of question because it gets at graphing, it gets at summarizing graphs, and it gets at comparing distributions. So here I have an example. They took people's pulse rates before and after they did a cognitive test on them. So pulse rates before and after giving a test. Okay, so we're going to compare the distributions. Oh, actually, it was a new drug. Sorry. We're going to compare the distributions of pulse rates before and after administering a new drug. So it could be a new drug, it could be giving a test. So in order to compare this, we want to look at it as a graph. And that's really the beauty of a stem and leaf plot, is that we can have the numbers and we can have a graph. So let's look at this before. We can kind of sketch this little thing over it. And I would say that I would like to ski off this way. So that means that the pulse rates are skewed right. And then remember the SOCs. We'll go more into detail about the OCS later, but for now let's kind of give an estimate. We'll say there may be an outlier at 146. And then centered. Where is this centered, right? It's centered somewhere around here. So we'd say it's centered around 95. And then what about the spread? And it's spread between, let's see, our lowest number is 86 and is spread between 86 and 146. Okay? So now, in order to be able to compare them, we also have to look at the before. But if we were to turn it just on its side, we would see that it's kind of like the opposite way, right? This looks like you'd want to ski down this way, which would be ski left, but we always want our number lines to be smallest to largest, right? So we'd want it to go 6, 7, 8, 9, but this is going 14, 13, 12. So you kind of need to like flip it in your mind, right? You want to get a mirror image. So we're going to go ahead and flip it. We'll actually flip it. So we've turned it to a mirror, and now we can say that the before is skewed right. So before is skewed right, and we say there's no outliers. And we can say that it has a lower center, right? Because now we're centered somewhere around 70. Lower center at around 70. And we can say that the spread is, it's a little hard to read in the mirror, but 68 to 110. So if we look back at what we said that it had a center at 95, so before had a lower center, and then its spread was 146 to 86, so our spread was 146 minus 86. So it was a width of 60. So a range of 60. Versus now, we have a range of 42. So a smaller range. So if you're ever asked to compare two graphs, you're really just going to give the socks of each of them, and then you'll kind of comment on, okay, well this center's a little lower, a little higher, or this had a lot of outliers, or this was skewed and that wasn't. But the easiest way to approach it is just give the socks of both of them, and then look at what you just said and compare them. Okay, so this says, students took a statistics quiz. The scores for the quiz are below. Describe the distribution of the quiz scores. Perfect, so we know that means we're going to want to give the socks. Okay, so first we should draw our little curve along it. And in this case, kind of shift it in your head. I would ski down this way, and we're always reading the number line, smallest to biggest. So we'll say that it's slightly skewed left. And remember that there's an old joke, statistics is never having to say you're certain. So if you think maybe it's skewed right, maybe it's kind of a little more symmetric, don't be super definitive. You can say it's kind of skewed right. It's a little skewed right, or it's almost symmetric. You know, you can be a little wishy-washy. That's okay, because something like a skew, it is kind of wishy-washy. This is kind of skewed right. It's not it's kind of skewed left. It's not really skewed left. So be okay to put those other words in there that are kind of saying, yeah, it's a little skewed, but it's not totally skewed. So we have it slightly skewed left. It's doesn't look like there's any outliers, so we'll say no outliers. And we can say it's centered. So it's probably centered, right here's the peak of the hill. We'll say it's centered around 42. And remember, in the next lesson, we'll talk more precisely how to calculate the center. So we'll say it's centered at 42 with a spread of 8, which is our lowest number, to 50. Perfect. Okay, let's do another example. Here are the IQ scores, the IQ test scores of a few AP Stat students. So make a stem plot of these scores. Perfect. So no problem. The first thing we need to do is figure out what is our stem and what's our leaf. So if you look, that's the smallest number, and that's the biggest number, which means we're going from 96 to 145. Okay, so remember that we're only using the last digit as our leaf. So for 96, we'd have 9 and 6. So then our biggest number is 14. So we'll have to cover all the numbers in between. So we have 96, then we have 110, 120, 122, 125, 126, then we have 130, oops, forgot the 3. I can count, I promise. We have 130, then we have 139, then we have 143, and 145. Perfect! And then we could even go on to say slightly skewed left, centered around 120, with a range of 96 to 145. Perfect. Okay, let's do one last example. So you're interested in how students in your class get to school in the morning. You take a survey and collect the following data. Okay, so it looks like 15 drive a car, 3 take the bus, 5 walk, 8 ride a bicycle, and 1 rides a skateboard. So construct a bar graph of your data. So if this had just said, construct a graph of your data, you should have right away known that this is categorical data, right? Because these are categories, car, bus, walking. You can't put that in any particular order. So if we were to construct a graph of this type of data, we'd really only have 2 options. We'd have a bar graph or a pie chart. And pie charts are really hard to do by hand because it's really hard to figure out like what percent of the slice kind of fits your data. So I really don't recommend making a pie chart unless you're explicitly told to make a pie chart. So we'll make a bar graph. So remember that a bar graph is going to have the categories down here. So we'll have car, bus, walk, cycle, and board. Okay, and then we're going to do this, we can do this as counts or we can write this as percents. So if we were to do this as percents, so first we have to figure out how many students we have here. So we have 15 plus 3 plus 5 plus 8 plus 1. So we have 32 students. So that means that 47% are riding in cars. And 3 divided by 32, we have, so 9.4%. Okay, so we have 9.4%, 15.6%, and then I'm just going to say 8 divided by 32, which was 25%, and then 1 divided by 32, which is 3.1%. And I see that that is missing. Okay, so that can be sometimes easier, sometimes harder. So we can make this as a percent or as a count, but just make sure we're saying what it is. So I'm going to make it a count just because it's a little easier to not deal with decimals. So I'll say count. And then I'm going to put my tick marks here. So I'll say 5. Actually, let's just have it go by 1. That might be easier. Or 2, 4, 6, 8, 10, 12, 14, 16. Okay, so we have our counts. Now we're going to make our chart. Okay, so we know that car is 15. We know that bus is 3. And remember that I have to make sure that my bars do not touch. You also want to make sure that the widths are about the same. That's also important. Okay, walk we had 5. Cycle we had 8. And then for boarding we just had 1. Perfect. Now, if we were to construct a relative frequency bar graph, it's going to be a little bit different. Remember, relative frequency, we want to know the frequency relative to everyone else. So that's where we're actually going to graph the percents. So it's going to look very similar, and the only thing that's going to change really is that now we're putting the percent over here rather than the value, or rather than the count. So we'll say relative frequency, and make sure that you're putting a percent sign, which shows that you're doing it as a percent and not as, say, a decimal. Okay, I'm just going to put car, bus, walk, cycle, board. Okay, so let's put a dash mark here at 50%, put one here at 25%, one at 75%. So I'm running out of space. 25, not 75. So for car, we had about 50%. Okay, for bus, we had about almost 10%. And remember, our bars are still not touching. That might be a little big. For walk, so this might be a lot easier on graph paper. For walk, we had about 15%. Let's make this a little smaller. For cycle, we had 25%. So this actually should be up here. Make this a little lower. So again, bar graphs are kind of an art project, and I am not super artsy, so apologize for my graph. And then we have 3% to get the idea. Perfect. So they're going to be really similar. The shape is really similar. All that's changing with the relative frequency is we're turning it into the percents, which remember we got by saying, okay, we had 32 people total, so 15 out of 32, 3 out of 32, 5 out of 32. That gives the percent in each category relative to the other categories. Great. So I hope to see you for the next lesson.